Okay, today in Honors Chemistry, we're going to talk about covalent bonds and molecular compounds. Once again, you might want to have a periodic table in front of you. When two or more atoms bond covalently, so they're going to be sharing electrons, we can say that a molecule is formed. Most covalent bonds are formed between nonmetals or nonmetals and hydrogen. Most will occur to have an octet of electrons, but there are some exceptions, and so we'll talk about exceptions later in this unit, and then when we draw Lewis structures, then you'll see that we can have different types of exceptions to the rule. Okay, a Lewis structure, so you can use electron dot to represent molecules. So for instance, if you have H2, so hydrogen has one valence electron, so and hydrogen needs two, and so if you bond it to another hydrogen, these two electrons are shared between these two hydrogens. They go back and forth through the orbitals. Another way of drawing that instead of two dots is you can put a single line, and that represents a single covalent bond. That means the electrons are shared between these two. For fluorine, fluorine's a little bit different in that fluorine has 7 valence electrons. And if another fluorine comes alongside, okay, now this fluorine has access to 2, 4, 6, 8. This fluorine has access to 2, 4, 6, 8. Another way of drawing that is to just draw a line between them. That represents the pair of electrons that's shared. And then you can do these either as lines or as dots. I'm going to go ahead and do them as dots. Okay, so we can say fluorine has one shared pair of electrons or a single bond, and hydrogen also has one shared pair. Single bonds are called sigma bonds, and you can write sigma. It's a Greek letter sigma, and it looks like that. And then each fluorine also has 3 pairs of electrons that are not shared, and we call these unshared. So for fluorine, this is the shared pair. Hydrogen, this is the shared pair. And then each fluorine has 3 pair of unshared electrons, 3 pairs. An unshared pair is a pair of electrons that is not involved in bonding and that belongs exclusively to one atom. So this fluorine has 3 unshared pairs. This fluorine has 3 unshared pairs. Now there's something called structural formulas. I'm just going to mention to you and show you what a structural formula is. We're not going to use them in here because when you start talking about molecular geometry, you're missing some important parts to help you determine what type. But a structural formula will indicate the number, the kind, the number, and arrangement and bonds, but it does not show you the unshared pairs of electrons in a molecule. Okay, so for instance, fluorine structural would look like this. Okay, so then you do not see the unshared pairs. So you can't do your electron count. So this is what structural is. We're not going to actually do structural in the classroom. Okay, so let's go through some steps for writing Lewis structures. Some books do it differently. This is just what works for me. So number 1, you're going to determine the total number of valence electrons using the formula. You will arrange the atoms to form a skeletal structure for the molecule. If carbon is present, it will always be the central atom. Now sometimes you can have 2 carbons that both act as a central and you just bond them to each other. Otherwise, the least electronegative atom is central. Except hydrogen, you can never have hydrogen as a central atom because it would give it too many electrons. Then connect the atoms by dashes, and the dashes will represent single bonds. Oftentimes, the central atom is the first atom in the formula. Not every time, but most of the time you're pretty safe in assuming that, unless, once again, it's hydrogen. You will subtract 2 electrons for each single bond you used in step 4 from the total number of electrons calculated in step 3. You'll divide this number by 2 to determine how many pairs of electrons are available for use. Place these pairs of electrons or pairs of dots around each atom so that most atoms have 8 electrons and 8 valence electrons, and hydrogen has 2. Count the electrons in the structures to be sure that the number of valence electrons used equals the number available. So you never want to have extra electrons that you've pulled in that you cannot account for. If there are too few pairs to give each atom 8 electrons that need 8, change single bonds between atoms to double or triple bonds by shifting unbonded pairs of electrons as needed. So we'll talk about this when we get into double and triple bonds. Okay, so the best way to do this is just to do some practice problems. So we're going to draw CH3I, which is idomethane. We're going to draw NH3, which is ammonia. And then we're going to draw H2S, which is hydrogen sulfide, or you may know that also as hydrosulfuric acid. Okay, so let's take CH3I first. Okay, so carbon has 4 valence electrons. Hydrogen has 1, but you have 3 hydrogens, so that gives you 3 electrons you're adding. And then iodine has 7. So what I do is I write the number of valence electrons available above each element, and then I add them up. So we have 14 electrons available. Okay, typically the first element in the formula is going to be your central. If carbon's present, it has to be central. So we're going to put a carbon, hydrogen, hydrogen, hydrogen in any order around, and then an iodine. Okay, so we're going to bond, 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 bond. These are single bonds. They each account for 2 electrons. So we have used 2, 4, 6, 8. So we say 8 used. That will leave us with 6 electrons left over. Now, I typically place my leftover electrons around my terminal atoms, or those atoms bonded to carbon first. Remember, you will not give hydrogen anymore. This represents 2 electrons. That is all this hydrogen can handle. The same for this one. So we're going to take 6 divided by 2 is 3 pair. We're going to put our 3 pair around iodine. Okay, after you do this, go back and count to make sure, count how many electrons you have used and make sure it's what you had available. So we have used 2, 4, 6, 8, 10, 12, 14. We had 14 available. Then check to see if everybody has what they need. This hydrogen has 2, this hydrogen has 2, this hydrogen has 2, this carbon has 2, 4, 6, 8, and this iodine has 2, 4, 6, 8. So this is the Lewis structure for CH3I. If you want to put it on pause and try the next 2, and then join me back. Join back to me. Okay, so nitrogen has 5 valence electrons, hydrogen has 1, but we have 3, so that gives us 8 electrons available. Nitrogen is going to be our central atom. We're going to put hydrogen, 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 bond, 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 2, 4, 6, 6 electrons used. That leaves us 2 left over, or 1 pair. Remember, we cannot give hydrogen anymore, so the only place to place these 2 are on this nitrogen. In this instance, we would call these lone pairs, but we'll talk about that when we get into molecular geometry. And I have not completely drawn this structurally correct, or the geometry correct, but we're going to go with this for right now. So we have used 2, 4, 6, 8 available. This hydrogen has 2, this hydrogen has 2, this hydrogen has 2, and this nitrogen has 2, 4, 6, 8. So this is the correct Lewis structure for ammonia. H2S is our last one. So we have 2 electrons for our hydrogen. And we have 6 valence electrons for our sulfur. So that gives us 8 electrons available. Okay. Remember, hydrogen can never be in the center, so we're going to put sulfur in the center. We're going to bond to hydrogen. We're going to bond to hydrogen. Single bond, single bond. We just used 4 electrons. That leaves 4 left over, which is 2 pair. So we're going to put the 2 pair on sulfur. We have used 2, 4, 6, 8 available. Sulfur has 8, and each hydrogen has 2. So that is how you do Lewis structures for just plain molecules. Okay, then you can also do Lewis structures for polyatomic ions. And this says also do structural. We're not going to do structural, so I'd just forget about that if I were you. Okay, so polyatomic ions. So remember, you have a list of polyatomic ions that you have learned. So polyatomic ions are made up of elements that are covalently bonded, and then they have a charge, okay? And then if you put this polyatomic ion with the hydrogen is going to be ionically bonded to this. Or if you put calcium with this, calcium would be ionically bonded to NO3, but the N and the oxygens are covalently bonded. Okay. To do the Lewis, you're going to use the same rules we just used, except for you're going to take into account the charge. If it is negative, for each negative charge, you're going to add 1 electron. And if it's positive, which the only one we work with is ammonium, you're going to subtract 1 electron for each charge. Now, this is important. When you are finished drawing the Lewis structure, you must put your polyatomic ion in brackets and then put the charge outside. If you don't, then you have drawn a molecule and it would be incorrect. Okay, so we're going to draw the Lewis structure for PO43 minus, and I'm going to do it on this sheet since I have more room. So this is our phosphate ion. Okay, so phosphorus gives us 5 valence electrons. Okay. Oxygen gives us 6, but we have 4, so 4 times 6 is 24. And then this 3 minus means that 3 electrons were also used, 3 extra electrons, so we have 3 more. So that gives us 29, 32, if I'm not mistaken. Okay. So phosphorus is going to go in the center. We have 4 oxygens. We're going to bond to it. Bond, 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 bond. So we have used 2, 4, 6, 8 electrons. That leaves us 24 or 12 pair. So we're going to do 1 pair, 2 pair, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we have used, let's count how many electrons we've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32. Check to make sure everybody has what they need. This oxygen has 8, 8, 8, 8, and then this phosphorus has 8. So this molecule, this polyatomic ion, is drawn correctly, so you will put it in brackets and then put the charge on the outside. If you do not put it in brackets, that means you drew PO4 and you drew it incorrectly. Okay, so that's how you draw polyatomic ions. Okay, sometimes compounds will form multiple bonds to satisfy their electron requirement, for lack of a better word, and multiple bonds are going to be double and triple bonds. So, and there are certain elements that tend to form double bonds and triple bonds more than other ones. So if you've got carbon, nitrogen, and oxygen in your formula, then think that could be making a double or triple bond at some point in the drawing. Okay, double bonds occur when covalent bond, it's a covalent bond produced by the sharing of 2 pair of electrons between 2 atoms. Whenever you have a double bond, one of those would be a sigma, and then the other is a pi, the Greek letter pi, which is a bond in which the electron density is concentrated above and below the line that represents the bond joining the 2 atoms. So your book shows you what a pi bond looks like. All 4 electrons in the double bond belong to both atoms. A triple bond is a covalent bond produced by the sharing of 3 pair of electrons between 2 atoms. And in a triple bond, you'll have 1 sigma and 2 pi. In a double bond, you will have one of those will be a sigma, and then the other one will be a pi. Okay, so we're going to draw the Lewis structure for CH2O, which is methanol, and then CO2. Okay, so just like we did earlier, we're going to do our electron count. Okay, so carbon gives us 4 valence electrons. You have 2 for your 2 hydrogens, and then oxygen gives you 6. So that gives us 12 electrons available. Okay, carbon is central. We're going to put a hydrogen, hydrogen, oxygen, bond, bond, bond. We've just used 2, 4, 6 used. That leaves us 6 left over, which is 3 pair. I give my terminal atoms, those bonded to my central, the electrons first. So we have 1, 2, 3. So we have used 2, 4, 6, 8, 10, 12, 12 available. This hydrogen has 2. This hydrogen has 2. This oxygen has 8. But this carbon does not. It only has 6. Carbon has to have 8. So what you can do is you can take any one of these pairs of electrons that are around oxygen, and you can move it in and make a double bond. And so now we've still only used 2, 4, 6, 8, 10, 12. Okay. Now this oxygen still has access to 8, 2, 4, 6, 8, and this carbon has access to 8. Okay. And so this is a double bond. And so if I said how many sigma and how many pi bonds are in this drawing, you would say there's 1, 2, 3 sigma and then 1 pi. Carbon dioxide has 4 for carbon and 12 for your 2 oxygens. That gives you 16. So we're going to put a carbon, an oxygen, oxygen, bond, bond. That gives you 4 used, and so that leaves 12 electrons left over, or 6 pair. 1, 2, 3, 4, 5, 6. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 16 available. This oxygen has 8. This oxygen has 8. This carbon only has 4. Always check that. So we know carbon is going to have to have 8. So we're going to transfer one of these pairs in and then one of these in. Now, what we could do is there's actually another drawing we could do, and then to decide which one is the drawing you should use, you do something called formal charge, and we're not going to do that in here, okay? Okay, so we've still only used 2, 4, 6, 8, 10, 12, 14, 16, 16 available. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8, and this carbon now has 8. So in this molecule, you're going to have 2 sets of double bonds. And if I said how many sigma and how many sigma and how many pi bonds are present, you'd go, there are 1, 2 sigma and 2 pi bonds. Okay. Now, covalent bond strength depends upon how much distance separates the bonded nuclei, which is called bond length. And as the number of shared electron pairs increases, bond length decreases. That simply means the 2 atoms are pulled in tighter, and bond strength therefore will increase along with bond energy. So if you have a triple bond, the atoms are going to be very close to each other. They're going to have short bond lengths, and it takes a lot more energy to break them. So double bonds are shorter and stronger than single, and then triple bonds are the shortest and strongest and have the highest bond energies of the 3. Now, there's another thing we need to talk about for a second. It's called resonance. So sometimes you'll have a molecule that there's more than one drawing that you can do for it, and so we say it has resonance. So resonance occurs when there are 2 or more correct Lewis structures to describe a molecule or a polyatomic ion. You need to be thinking about, is resonance possible if when you draw your when you draw your molecule, if it contains at least one double bond in it and a single bond. So then there's a chance it could have resonance. Okay, so we're going to draw the resonance structures for O3, which is ozone. So we have O3. Let's just use my other sheet. That gives us 18 electrons available. 3 times 6 is 18. Obviously, oxygen's going to have to be your center. We've just used, by bonding 2 oxygens to it, we've used 4 electrons. So that leaves us 14 or 7 pair. 1, 2, 3, 4, 5, 6, 7. Okay? So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 18 available. This oxygen has 8. This oxygen has 8. This oxygen has 6. Okay, so we know this one needs another one, right? So what we can do is we can take any one of these unshared pairs and move it in. But then who's to say it couldn't have occurred like this? Have one of the unshared pairs from the other oxygen come in. Okay, so that means that the double bond can form between the first and second, or the second and third. And so we say there are 2 resonance structures, so you show an arrow going back and forth, so it will resonate or go back and forth between these 2 drawings, or these 2 molecular images. Okay, so always check. Now sometimes you can have 3 resonance structures, but whenever you just need to always draw the number that is applicable to the drawing you're doing. Okay, so that is resonance. There's a lot we're talking about in this section. Okay, the last thing I want to talk about real quick are exceptions to the octet rule. So if you have an uneven number of electrons, we sometimes call these free radicals. So for instance, if nitrogen is your central atom, So if you have NO or NO2, nitrogen has an odd number of valence electrons. And if you only have one nitrogen, then you're going to have an uneven number of electrons. So that would be called a free radical. Your central atom can have fewer than 8 electrons. So if you have a hydrogen bonded to another hydrogen, then it's going to have less than 8 electrons. Beryllium only has 2 valence electrons. So if it's your central atom, then it's going to only have 4 around it. The same for magnesium. Depending on who you put magnesium with, it can actually make a polar covalent bond. Boron is going to be good with 6 because it only has 3 valence electrons, and the same for aluminum. And then there is something called an expanded octet, and so this is where your central atom will have more than 8 electrons around it. This will occur when the central atom is from the 3rd period or below. So elements from the 3rd period or below, if they're your central atom, can exceed the octet rule. And the reason this occurs is because they can place extra electrons in their empty d orbitals. Elements in the 2nd period cannot, so if you had like nitrogen as your central atom or oxygen, it could never have an expanded octet because there's no 2d orbital. Remember, your d start at your 3rd energy level. The central atom is a nonmetal from period 3, so if phosphorus, sulfur, or chlorine, well, if phosphorus or arsenic or antimony is your central atom, then you're going to have an expanded octet. Then if sulfur, selenium, tellurium, you'd have an expanded octet, or if chlorine, bromine, or iodine were your central atom. Okay, so in molecules of this type, the terminal atoms are most often a halogen, fluorine, chlorine, bromine, iodine, and then sometimes oxygen. Okay, so that ends this section. So now you can do your homework set 2. And remember, if it's not in your notes, then you need to go to your book. And probably you need to be reading your book anyway because it's a little bit more organized than in how it presents it.